Okay, so here's a video about 5.1. So this section is about approximating areas. So typically we have a function, and I graphed some function from x equals a to x equals b, and we would like to find this area. Yeah, I don't want to shade it, but it's the area that's underneath the curve and above the x-axis and in between these two lines. And the way we do that is we break that area into small pieces that are almost rectangles, right? This is like a skinny, tall rectangle. What we can do is, I can choose a height for this rectangle. Of course, it's not really a rectangle because the top isn't flat. But I can choose a level to cut it off. Like I could do it here, or I could do it here, or somewhere in the middle. So maybe I'll draw it here. And then I choose a height for this rectangle. And yeah, I choose a height for each one. Like maybe for this one I can choose this height. Some of the rectangles might be above the curve, some of them, like this one, some of them might be below the curve, like this one. Sometimes you choose the right endpoint for the height, or the left endpoint, or the midpoint. And then you just add up the areas of those rectangles once you choose how to draw them. This is representing a sum. This is a Greek letter sigma. It looks like a capital E, but it's not. This means we're adding up a bunch of numbers. This is the height of rectangle number I, and this is the width of the rectangles. So like this is delta x, this is also delta x. Each rectangle has width delta x. And of course, this is just an approximation of the area. These rectangles aren't it's not really the same area that we're trying to find. It's just an approximation. But if you do the limit, as you use more and more rectangles, you can imagine these rectangles getting skinnier and skinnier, and you use more and more of them, and the approximation gets better. And the limit, as the number of rectangles, because n is the number of rectangles, goes to infinity, that's the exact area. Okay. So let's do an example. We're going to approximate the area underneath this curve. This is just y equals x squared. We're going to use n equals 3, so there's 3 intervals, and we're going to use right endpoints. So let me say what this means. Oh, and then we're going to use midpoints, but first I'll use... For right endpoints, I'm just going to draw this picture again. So first of all, I'm doing an interval from -1 to 2, so that's a length 3, and I'm using 3 intervals, so that means each interval is going to have length 1. So my first interval is going to go from -1 to 0, my second one goes from 0 to 1, and my third interval goes from 1 to 2. So I'm going to have a rectangle whose base goes from here to here, and then I have to choose the height of that rectangle. When it says use right endpoints, that's telling you how to choose the height. So actually, this rectangle, it's a little bit funny, but the right endpoint is here. We're talking about the interval from here to here. So this is the right endpoint. So here, this would be a height of 0, because this is the graph is going through the x-axis. So this is like a rectangle whose height is 0. It's just a super short rectangle. The next interval would go from here to here, and so this is the right endpoint, so this is going to be the height. So this is my second rectangle, and this is my third rectangle because I use the right endpoint to determine the height of the rectangle. Right? But so drawing this picture isn't strictly necessary to solve the problem. I just wanted to show you what we're doing. What I really want is an approximation of the area. But, well, drawing the picture does help. It's not necessary, but the first rectangle has an area 0 because the height is 0. The second rectangle has a height of 1 and a width of 1. The third rectangle has a height of, well, this would be 4, right? Because this is the graph of y equals x squared, and this is x equals 2, and that's how we drew the height. So there I get 5. And by the way, there's some questions on the online homework about, scratch that. I'll mention that later. For now, let me move on to the midpoints. So yeah, even though it's not strictly necessary, I'll draw the picture again. I'm still using 3 intervals, so the bases of my rectangles are going to be the same. The heights will be different, though. So to determine the height of each rectangle this time, I'm using the midpoint of the interval. So the interval from here to here, the midpoint would be here at -1/2, because this is -1, this is 0. So that is going to be the height of my rectangle. Similarly, from here to here, my interval from 0 to 1, the midpoint is 1/2. So that is going to be the height of my rectangle. And then the interval from 1 to 2, the midpoint would be 3/2. So that is going to be the height of my rectangle. So the new estimate I get for the area is, well, my first rectangle has a width of 1 and a height of what? So the height is just whatever the height was, because I used the midpoint, -1/2. So the height is just whatever this y coordinate is. In other words, it's f of -1/2 times the width plus f of the next, and the next midpoint, which would be 1/2 times the width of that rectangle, plus f of 3/2 times the width of that rectangle. And all these rectangles have a width of 1. And yeah, f of x, this is just x squared, so this is 1/4 plus 1/4 plus 9/4, so 11/4. Okay. Let's do a different example that is not really about areas. This is about speed and distance traveled. Say we have a table of readings telling us the speed after t seconds, and we would like to estimate the total distance traveled. And we want an upper estimate and a lower estimate. So here's how we're going to do this. If you notice, the velocity is always just going up. Like it starts at 1.1 and then it goes up and up and up and up and up. So here's how I'm going to give an upper estimate on the amount of distance traveled. In the first 2 seconds, it looks like we went between 1.1 and 3.2 of our velocity. If I want an upper estimate, I'm going to assume that we went the faster speed during the whole 2 seconds. And I know that's not true. During these 2 seconds, in the beginning we were going this fast, in the end we were going this fast. But if I want an upper estimate, I can just act like we were going this speed for the whole 2 seconds. So I would go 3.2 times 2, because that's for 2 seconds. And then between second number 2 and second number 4, between times 2 and 4, I went between this speed, and for an upper estimate, I'll just assume we went this speed. So 4.3 times 2. And then from time 4 to time 6, I'll assume we went this speed. So 5.1 times 2. And right. So yeah, so getting a little bit lost here. This was from 0 to 2 seconds. This is from second 2 to 4. This is from 4 to 6. Okay, I'm not lost anymore. I need to do 6 to 8. Between second 6 and second 8, I will assume I went this fast. So 7.2 times 2. And then I just need to do t equals 8 to t equals 10. So I'll do 8.9 times 2. And that's whatever it is. I will tell you in just a second. Okay. That's 3.6, 4.3, 5.1, 7.2, 8.9. I multiply each one of those by 2 and I add them up. 58.2 feet. That's my upper estimate. For my lower estimate, you can probably guess what I'm going to do. Between time 0 and time 2, I went between this speed and this speed. So if I want a lower estimate, I'm going to take the smaller speed. So I'm going to take 1.1. And then you can see how this is going to go. So I'll start going faster. From 2 to 4, I'll take this speed. So 3.2 times 2, 4.3 times 2, 5.1 times 2, 7.2 times 2. And that's it. Right. This was time 0 to 2. This is representing 2 to 4. This is 4 to 6. This is 6 to 8. And this is 8 to 10. It might be a little bit tempting to use this last number to say 8.9 times 2. But we don't do that. We're done. We got all the intervals. We got from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. Between 8 and 10, we assumed that we went this speed. So this number doesn't play any role in what we're doing right now. And this is just, again, that's just whatever it is. 42.6. So the actual distance traveled is somewhere in between 42.6 feet and 58.2 feet. Okay, other than that, in this section, there's a couple of problems that ask you to evaluate sums, and this is going back to that funny-looking sigma notation. This is not hard. It's just all you have to do is you just have to know what it means. So this is a sum. This starts at k equals 2, and it goes up to 5. What you do with this is you start by plugging in 2 here. And then I'm going to plug every number up until I hit 5. So 3, now I'm plugging in 4, now I'm plugging in 5, and then I stop because I hit the top number. And then you just add them all up. This literally means you plug in every number from here to here, and you add up the result. So this is 4 plus 9 plus 16 plus 25. Can I do this in my head? So this 4 and 16 makes 20. That makes 45. So I get 54. So there's a few like that, and it's different formulas, but you do them all the same way. You plug in starting at this number and ending at that number, and you add up all of the results. This sigma notation, it's useful because for the stuff that we're doing right now, we're adding a lot of things. Like in the last problem, we added a bunch of things, and when we were finding approximations for the areas, this involves adding up a bunch of areas of rectangles. And that's how we initially wrote our approximation for the area. This is a sum where the things that you're adding up are areas of rectangles. So that's why we're talking about this stuff right now. But it's not that hard, you just have to know what it means.